CNNs. So thank you for coming.
Thanks. Thanks for the nice introduction. Yeah, and thanks also, David, for the previous presentation. It's gonna save me introducing some concepts. Yeah, I'm Gabriele Cesa from Qualcomm Research and University of Amsterdam. I'm gonna talk about steerable CNNs, as mentioned before. Before jumping in the technical part of the talk, let me briefly thank all my collaborators over the last few years, which contributed to all the works I'm gonna present today. So in particular, Maurice, Leon, Maxime, and Lars. So yeah, let's start. I will skip basically all the first part about why we do equivariance, because David made like a good presentation before. I hope you're convinced that data can have symmetries and it can be interesting and useful to exploit them to build inductive biases in our neural network. So let's just go directly into the question, how do we do that? This talk is very orthogonal to what was presented in the previous one. It's a kind of different approach to build equivariant networks. Although as presented by the last paper of David, there's some connections, some interesting connections being developed now. Okay, let me first start from convolutional neural networks. You're probably all familiar with normal convolution and standard convolutional neural networks, which are known to be translation equivariant because of the use of convolution. But as we know, they're not really equivariant to other transformations. So if we rotate our image and then feed it in a convolutional neural network, we get some results that some output images that don't really rotate properly, but they deform in some unpredictable way. So how do we achieve other type of equivariances? Let's roll back 1 second and start from the basics. So what is convolution? In a convolution, we take our image, like this lizard, one learnable filter, and then we apply this filter at different locations of the image to generate a new image. For each location where we place our filter, we get a new response, and therefore this output image. The idea of a group convolution basically generalizes this by not only using translations, but other operations like rotations. In this case, essentially, this boils down to do convolution with 4 rotated versions of the same filter. We only learn one filter, we rotate it 4 times, we do convolution with each of these filters independently, and now we essentially get 4 different output images, which we can think about just a 4 channels output feature map. I'm not going to spend too many slides on group convolution. That's just to get to steerable CNNs. But the result is that this is equivariant because the 4 channels output contains an activation for every type of rotation and translation. So when the input rotates, no information is lost in the output, but all these activations just permute and move around in the output features. More precisely, we see that a rotation of the input leads to a rotation of the output pixels, right? Like one would expect, but also a cyclic shift of the 4 output channels. Keep that in mind. This is like the basic idea of group convolution. This is actually what we typically call lifting convolution, because it doesn't really do convolution over the full group, but we take in input just a scalar image, like a grayscale image, but we get in output a feature map over the full group. The same idea can be used to build group convolution or in the intermediate layers of a deeper network, which have to actually process features produced by the lifting convolution. The idea is pretty similar. We just have to rotate rather than scalar filters, like in this case. We have to rotate kind of 3-dimensional filters, which have a rotation resolution, like here. And we do so using the same kind of type of transformation. I think that the intuition with lifting convolution is more useful, and I don't want to spend too many words on the technical details of that. So let me conclude the quick introduction to group convolution. Group convolution is a very generic and powerful framework that allows us to build a wide variety of equivariant networks. So why do we need the next 50 minutes of the talk? While the abstract formulation is very general, there's some challenges that arise during implementation. This is the equation of group convolution, but as you see, right, the formulation essentially requires you to enumerate and apply every transformation you care about to your filters. And if you care about a very large number of transformations, or even like a continuous group, like a continuous rotations, this becomes quickly very hard to implement and requires some form of a discretization, which can lead to aliasing or like some kind of artifacts. And also this kind of formulation doesn't allow one to work with things like vector fields or tensor fields, like the ones that David was presenting before. So we try to do one step back from group convolution. Let's rethink a bit what is going on here. Again, let me repeat myself. We have an image. We learn a single filter. This filter can be very generic, unconstrained, but then we have to repeat it 4 times to generate a complete feature map, which is equivariant to rotations. If instead of using a very generic filter like here, instead we make use of a filter, a rotation invariant filter, isotropic filter, we see that we actually don't need to do 4 different convolutions, but a single convolution with this filter already generates a feature map, which is actually just grayscale image. It's like a 1-channel feature map, but it is equivalent to continuous rotations. And that's just given by the fact that the filter itself is rotation invariant. Of course, this comes with some loss in expressivity, because we cannot make use of every possible filter. These are a very small subset of the possible learnable filters. But this could be already like a different trade-off. Isotropic filters are a special case of the generic family of steerable filters. These are filters that can be rotated, continuously rotated, by just linearly interpolating some set of basis filters oriented at certain fixed orientations. For example, you might recognize here the classical filters used for edge detection in computer vision, which are like directional derivatives of Gaussian filters. And they have the property that basically a rotation by theta of this filter is equivalent to linearly combining the horizontal and the vertical filter weighted by the sine and cosine of theta. It's easy to prove, but it's not the point here. Why is that interesting? Because now we don't need to actually do convolution with infinitely many rotated versions of this filter, but we can just consider these 2 orientations. And then because of linearity and associativity, we can recover the activation we would have gotten from different orientations just by linearly combining the responses of these 2 filters. Let's make this a little bit more visual, and imagine we take these 2 horizontal and vertical filters and place them on one patch of our image. This gives us 2 numbers, right? The 2 responses of the filter, which we can interpret as the 2 coordinates of a 2-dimensional vector attached to this point. And because of this steerability property, what happens is that if we now rotate this patch under our filters, this 2-dimensional vector rotates around its center. More precisely, by rotation, I mean it's a 2-dimensional vector that is being multiplied by this 2x2 rotation matrix. Again, I'm not going to prove this, but it's quite intuitive. It's like a couple of lines. If we look at the bigger picture, so we actually do convolution on a full image, we don't get anymore a single 2-dimensional vector, but now we get a vector field like the ones we saw before. And the vector field now doesn't just transform by rotating the image, but transform also by rotating each vector attached to each pixel. So again, doing convolution with these filters produces a vector field where a rotation is given by actually moving the pixels around in the image, like normal image, but also by multiplying each individual 2-dimensional vector by this rotation matrix. All right, so these were like 2 examples of steerable filters, but there's many more of them. Some of you might be familiar with circular harmonics or even spherical harmonics in 3D. These are all kind of filters that satisfy the same property. And as you can see in the image, we are not restricted to simple frequency 1 or frequency 0 filters, which are isotropic or like the derivative of Gaussians, but we can also use higher frequency filters The difference is that the output vector field will rotate not by a simple rotation matrix, but will rotate with higher frequencies. A similar idea happens in 3D where one uses spherical harmonics and Wigner matrices. If you're familiar with that, otherwise we can stick with the two-dimensional case. It's sufficient. All right, so that's the very quick introduction to group convolution and steerable filters. Let's now move towards steerable CNNs. And to do that, we need to change a little bit how we think about features in a neural network. That is, rather than thinking about features as multidimensional tensors, I want to interpret them as kind of continuous signals which associate to each spatial location, so to each pixel, a d-dimensional feature vector. The reason why we do this is that now we can interpret features not as tensors, but as vector fields, similar to the output of the steerable filters. The other small change I do is that from now on, I will use the group G to refer only to the rotation or reflection, but the point preserving symmetries, while translations, I always assume translation equivariant is given by the fact that we use convolution, so we don't really care about that much anymore. Now, a feature field in general is like essentially a vector field which transform according to certain transformation laws, and that basically define how the group G transform these features, these vector fields, and that is given by, as we saw before, a transformation of the pixel coordinates. So we see here the group G transform the coordinates where we sample our field or our image, but also by a rotation or like a transformation of the channels of the feature vectors. And that is defined by a representation of the group. Sounds maybe a bit abstract. So concretely, we can look again at the previous examples. If we do convolution with isotropic filters, we get scalar images, and the rotation of a scalar image, it doesn't change the color of the image. So that is basically, as we see here, like we just multiply by the value 1 always. That is a trivial representation, if we want. While the vector field we saw earlier, as we know now, transform both by moving the pixels in the image, right? But also by multiplying each individual vector by this 2x2 rotation matrix. And that's the standard representation of the rotation group. Let me just make this a little bit more formal. A representation is just a map that associates to each group element an invertible squared d by d matrix. And with some constraint, these maps must basically be compatible with the way the group elements combine. That's all I want to say about it. And without loss of generality, we will assume that these matrices are always orthogonal. That is possible because we work with compact groups and makes everything much simpler. So yeah. Another special case of steerable features is the output of the group convolution we saw before. That looks a bit surprising because now we have very generic filters, so we just get the output of convolution with 4 filters. But we can think about actually this output feature map as a 4-dimensional vector field, associating to each pixel a 4-dimensional vector, which rotates not by a 2x2 rotation matrix, but by these 4 permutation matrices, which essentially implement this cyclic shift along the channels. Why did we introduce all of this when group convolution is just a special case? That's useful to go the next step, which is going beyond just 4 rotated filters, but we can pretend that we can actually do convolution with infinitely many rotated filters. So in this case, rather than getting a channel for each of the 4 rotations, we get a channel for each of the angles between 0 and 2 pi, right? So all the rotations in the special orthogonal group of dimension 2. Of course, we cannot do this, right? But let's pretend we can do that. Then at each location t, right, so each pixel, we have essentially a continuous function over the angles theta between 0 and 2 pi. This is a continuous function living in an infinite dimensional space. How do we parameterize such functions? In this case, Fourier transform is often the most oh, the corner is kind of hidden. Can I move this somehow? Okay, if you can press in that. Yeah, thanks. So yeah, the most natural choice is taking a Fourier transform of this function. And the benefit is that we probably don't care about all the finer details of this continuous function, but we care mostly about the low frequency components of that, which contain most of the information. So we can now work with a finite dimensional space given by only the first few Fourier coefficients rather than the whole continuous function. The second interesting part is that the Fourier transform is a linear function, and so is also the convolution. So we don't need to actually go through this infinite dimensional space produced by infinitely many convolution layers, right? But we can directly take the angular Fourier transform of our filters and work with these steerable filters we saw before. You might recognize the circular harmonics, and you can basically show that this is equivalent to do convolution with a Fourier transform of our filter. So this is why we care about these steerable filters we showed before. Now, rather than thinking about each of these steerable filters as an independent convolution, again, we like to stack all these features in a bigger vector field or feature field. This is operation of stacking is what we call a direct sum. So rather than looking at each of these vector fields individually, we look at a much bigger vector field containing the stack of all of them. But it's important to notice that each subset of them still transforms independently according to a different representation, right? Rotating with its own independent frequency. This is what we define as the direct sum of these representations. Notice that representation concatenate by stacking them along the diagonal of a bigger matrix, right? But this is very similar to what you might be familiar from, classical harmonic analysis for periodic functions, just with the rotation matrices rather than complex harmonics. All right, let me give a few more names here. What we worked so far with is called the regular representation of the group. The regular representation is basically the orthogonal representation of the group acting on the space of functions over the group itself. In the case of finite groups, this looks like the 4 permutation matrices we saw before, where basically we identify each axis in a 4-dimensional space with the 4 elements of the group, and then the group just permutes this axis. But when we work with bigger and continuous groups, we can leverage the idea of a Fourier transform, which is formalized by the Peter-Weyl theorem. Forgive me for the joke, but this theorem is the building block of the whole framework of steerable CNNs. So you're going to see the Peter-Weyl theorem popping up multiple times in the next slides. And essentially what this theorem states is that each compact group has a number of special small representations called irreducible representations, which essentially generalize your intuitive notion of frequencies. And they provide basically an orthogonal basis for continuous functions on the group. In particular, these are the irreducible representations of the rotation group, and you can recognize in their entries the typical cosine and sine basis you can use to expand any periodic function. This is the definition of our Fourier transform. We just have one learnable coefficient for each irrep psi and for each entry of the irrep because they are matrix valued. So that's how we write it explicitly. I care more about the general intuition, so don't worry too much about this equation. The Peter-Weyl theorem is a bit more complicated. What I'm going to lie to you for the rest of this presentation, because all of this is only true when we work with complex numbers. There's a few corrections one need to do when we work with real numbers. I'm going to pretend this is not the case. It doesn't change too much the formulation, just makes things a bit more ugly. There is also a bit more powerful version of the Peter-Weyl theorem because it does provide us not just a Fourier transform for functions over the group, but it actually gives us some kind of Fourier transform for any possible representation of the group. indeed, any representation row of our compact groups can actually be decomposed as a direct sum of irreps, like we see here, right? Up to a generic change of basis. In case of a regular representation, the change of basis is our Fourier transform matrix, but we can decompose anything. So irreducible representations are essentially the building block we need to describe every possible representation, and as we will see, also every possible steerable CNN, essentially. All right, enough mathematical background. Let's check where we are left. What we described so far is basically how steerable filters allow us to achieve continuous equivariance and replace our group convolution. We have only seen actually an example for the lifting convolution. We start from a scalar image and we go to features over the full group or a Fourier transform. But what happens in the intermediate layers of our neural network? What happens if the input has different type of is a different type of a vector field itself? This is kind of the central question to design steerable CNNs. So let me now look at steerable CNNs a bit from a more high-level point of view. When we build steerable CNNs, rather than, again, picking individual filters and then see how these filters, what kind of output these filters generate, we typically want to design them by choosing how each intermediate layer transform. In the same way as in a CNN, you choose the number of channels in each individual, each intermediate layer. And then we want to design layers which commute with their corresponding input and output representation or transformation law. If we do that in the proper way, the idea is that then we want, when the input rotates, then by induction, also all the activation at all the intermediate layers also rotate. So how do we do this? Well, that's essentially the question. We want to build first convolution layers that commute with respect to their input and output transformation laws, whether those are scalar and vector fields or other type of feature fields. And this was partially solved by previous works from our colleagues in Amsterdam. And basically, you can show that to achieve this, it's sufficient to use your normal standard convolution with your convolution filters, as long as the full convolution kernel satisfies this steerability constraint. Don't worry too much about this. We're going to see it multiple times again. But essentially, this is an equation that tells us the sufficient necessary condition to satisfy. So the question is, how do we parameterize all the filter that satisfy this equation? Before jumping in this part, I want to briefly mention that, of course, deep neural networks also include nonlinearities. There's a wide literature on what are the best nonlinearities and their pros and cons, but I'm not going to talk about this. I assume that these are available, but of course, it's something that a lot of people worked on for many years. All right, just to give a preview of what's the end result, if we build a proper steerable CNN with the right convolution layers and the right activations, we can now build a deep neural network, which is actually rotation equivariance. So the output contains, for example, vector fields and scalar fields. Compare this to the first image at the beginning of a normal CNN. The output of the neural network behaves like we would expect. All right, so the second part of the talk is going to be about how do we parameterize these convolution layers. First, how we do it exactly, so to achieve exact equivariance. And in the second part, how do we do it how do we relax these constraints, or how do we learn them? If someone has some question, maybe this is a good moment to take a small break before I dive in that part. Yeah.
Thank you for the talk. Quick question about the representation for the rotation. You showed, yes, rotation matrix. And for example, in computer graphics, we don't use those, we use quaternions because they are more stable and you don't have the risk of having a gimbal lock. Yeah. Maybe is it for this?
So that's also some variations of this could handle also quaternions as intermediate representations. Maybe that looks a bit more similar to what David presented before, but I need to highlight that the the problem here is different. Like in a computer graphic, you use quaternion as a way to parameterize the group itself. And that has all the continuity nice properties that doesn't produce, gimbal locks and so on. Here, we don't need to parameterize elements of the group. We never actually parameterize elements on the group. We parameterize features which transform under the group. So we never really encounter these singularity problems. So yeah, potentially you could use also quaternions. Those are actually projective representations. They are not real representations of the group, but the theory could be adapted to handle projective representations. I think some people did that. I don't see practical reasons in the sense that this works well, but like, it could be like an extension. It's just that it's not motivated by this same problem that people have in computer graphic. Yeah.
Hi, short question for the storyline. You showed the theoretical statements because your further slides are relying on these equations.
Yeah.
So, and how they are related to each other? Do you use Schur's lemma at some point in the next slides, or?
Yeah, I will use it, but I'm going to ignore the Schur lemma. I'm going to use the Peter-Weyl theorem because it makes things.
So you just use the direct sum decomposition, right?
Yes.
Okay.
Essentially, I use just this Peter-Weyl theorem, and you will see how. So far, I just state the two theorems we need, which is essentially the Fourier transform and the steerable constraint.
Actually, I was just asking myself, need the summons to be simple? So that's the reason I'm asking you are using Schur's lemma or not, because otherwise you don't need to assume that G is compact anymore.
Yeah.
You can have always the composition in the composables, but this is a different story.
Yeah. It's gonna get clearer in the next few slides, but I see your point. Thanks.
Any comments? No?
All right. Let me check the time. Okay. All right. So let's see how do we solve this problem, which is how do we parameterize in the most general way filters that satisfy this steerability constraint. Very high level overview of the strategy we're going to follow essentially is notice that filters are actually vectors in some vector space. It's the vector space of every possible convolutional filter, and so also are equivariant filters. So and there exists a linear projection operator that basically maps from this big space of all possible filters in the subspace of the equivariant ones. So what we're going to do is define this linear projection, then pick a basis for the domain of this projection, that is every possible filter, that we will pick a very convenient one, and then project this basis through this projection operator to find a basis for our equivariant filters. That's a very high level strategy. I want maybe you to keep in mind, and then we see a bit more the details of how that's going to happen. So first of all, the linear projection. The linear projection is essentially defined by the Reynolds operator, if you have heard it before. But otherwise, basically what we do is take a generic filter K prime, unconstrained, very free, and then we basically average it over the whole group by applying for each group element the kernel constraint. You can prove that the result of this projection actually satisfies the kernel constraint, and every equivariant kernel can be parameterized, is basically belonging to the image of this projection operator. So following this, the output of this integral is going to give us every possible equivariant kernel. Now, working with this current version of the constraint is a bit inconvenient because we deal with the matrices and we have the group G acting in multiple places. So it's a bit cleaner if we vectorize this. So these are, before we had a matrix valued filter, right? So with some input channel and output channels, we now stack all the columns of these matrices in a bigger vector. This is just a vectorization, and we use this identity given by the Kronecker product. So that basically tells us that the vectorization of the product of three matrices is equal to the vectorization of the matrix in the center, left multiplied by the Kronecker product of these two, right? And the Kronecker product is obtained by taking one matrix, right, B, and plugging it in each entry of the first matrix A to basically get a much bigger matrix. Doesn't matter too much. What you need to know is that this is kind of representing the left and right matrix multiplication, just as a one single matrix multiplication. Makes things a bit simpler and cleaner. So now we get this vectorized kernel constraint. Nothing changed so far. The next step is picking a basis for the input domain, right? For the space of all possible filters. And here comes back the Peter-Weyl theorem and the steerable filters we had before. Basically, by noticing that the space of all functions on Rn carries an action of our rotation group, we can rotate scalar functions. That means there is some kind of Fourier decomposition of that in terms of some steerable basis. That basically give us, like as we saw before, a bunch of filters or basis functions which we can group together and rotate together by just linear interpolation. Essentially, that means we have, like, I don't know, some group of functions at y, j, k indexed by a certain frequency and maybe a certain radial component k, and they satisfy the property that a rotation of them in a block is equal to just the basic version of them left multiplied by one irrep or one representation of a certain frequency. We use this now to expand our kernel, unconstrained kernel. So we use like very generic weights because we don't parameterize a scalar function, but we parameterize a vector feed. We don't need a weight for it. We don't need a single weight for each basis element, but we need a vector of them. So that's why we have this matrix for each basis steerable basis vector, which has a few components. We have like a number of rows for each output channel. So yeah, we just expand our unconstrained kernel in terms of this basis. But this property becomes pretty useful because if we plug this back in our constraint and do some manipulation, simplify, we can take basically our steerable basis out of the integral and also this sum. And we are left with a bit of a simpler constraint now. We have an integral. We have a matrix, we have a left multiplication and a right multiplication by two different representations. Again, we don't like matrices, we want to work with vectors. So we do, yet again, some vectorization. We do the same trick as before, right? But now we are left with the vectorization of our weight matrix, which goes outside of the integral. And in the integral, we are only left with a three ways Kronecker product or tensor product, if you're more familiar with representation theory. So that's it. Now, like, we have only one place where the group appear, and it's inside the integral. The drawback is that this looks like a very complex representation, but we can simplify things a little bit without loss of generality. We assume that actually the input and output representations are irreps, just because this way I can index them with some frequency index. So now we have to work with the frequency L, big J, small j, just for notation. And now we can simplify this three-way tensor product using, again, the Peter-Weyl theorem. This is just a very big complex representation, but it is still a representation which we can decompose somehow using irreps. If you know what I'm talking about, you might recognize the Clebsch-Gordon transform here, but otherwise we can just pretend it doesn't exist, and we just imagine we know this change of basis which we need to apply to obtain an irrep decomposition. Irreps could appear, different irreps for different frequencies can appear in multiple, with different multiplicity. Doesn't matter too much. This is a direct sum of many irreducible components which we know. And the integral now can be brought inside this direct sum and change of basis because all these terms don't depend on G. And the interesting part is that yet again here we recognize an integral over the over a function over the group, which should remind us slowly of one more time of a Fourier transform. Indeed, we can imagine we are just integrating our Fourier basis, which are the irreps, against a constant function. So we just make use of the fact all these Fourier basis and the constant function are orthogonal function. So when integrated against each other, they give us this delta function that selects only the frequency 0. This is basically a different way to derive Schur lemma, if you are familiar with that, but it kind of give us a Fourier interpretation of that, which is a bit simpler maybe. So yeah, what happens here is that now we have a very sparse matrix, which is like a diagonal matrix with just a few ones and 0 on the diagonal, selecting basically the invariant components. surrounded by a left and right multiplication by a change of basis, and then applied to the vectorization of all our weights. This is essentially our projection operator. We are just picking some of the steerable filters we started from to select those which satisfy the steerability constraint. This is a bit high-level abstract overview, but this actually leads to a very practical and efficient algorithm to parameterize any steerable kernel for any compact group G and arbitrary input and output representations. And that's what we implemented in our library in PyTorch a couple of years ago. And that's what we use to build our equivariant networks. To convince you of its generality, let me just quickly scroll through like a list of a lot of experiments. This can work in 2D. We work with the subgroups of the 2D isometry group. So we build networks which are equivalent to translations, 2D rotations, 2D reflections, and combinations and subgroups of those. And we can work with different type of intermediate representations or different frequencies. These are some experiments on variation of MNIST. We can do the same in 3D using subgroups of the 3D isometries that include 3D continuous, 3D rotations and reflections, but also the symmetries of the platonic solids, or just planar rotations around certain axes in 3D, or dihedral mirrorings in 3D, inversions and mirrorings in 3D, and again, every kind of combination of them. A small drawback of this approach that I ignored before is that while this is very general, it still requires someone to come up with the steerable basis I mentioned before. Like, we know there exists a steerable basis and a set of steerable filters parameterizing all our scalar filters, which is steerable, and that looks like spherical harmonics and circular harmonics if you work with the orthogonal groups. But if we want to work with subgroups and we are allowed only a finite number of this basis, it is quite tricky to design this basis on your own. So what we did in this work, which also David mentioned before, with Maxime, we instead choose to not design these filters by hand and solve the kernel constraint by hand, but we actually learn an MLP, which is only G equivariant, which is a much simpler constraint to satisfy using just short lemma. And then we parameterize the MLP to satisfy the kernel constraint. The rest of the neural network design is the same, but this basically allows us to build more powerful, better kernels when we work with the subgroups, which are not just SO3 or O3. And that is nice when we have smaller symmetry groups. Another drawback of the equivariance formulation so far is that we always assume we know exactly the symmetries of the global data. So we have like one group that acts over the whole data point or the whole image globally. So for example, we rotate the whole image. But this setting is is not as common when it comes to natural images. So if we look at this image, for example, the sky is always on the top and the ground is always on the bottom. So it doesn't make sense to use rotation equivariant networks. Still, at a local scale, we often have patterns which have a wider set of symmetries. Like look at these, the flowers. So this is one of the ideas we try to exploit in our works through the group restriction operator, which essentially just means building a deep convolutional neural network and have different layers equivariant only to the group we expect to see at the field of view of the neurons in that layer. So I don't know, the first layers are going to be equivariant to all the rotations because they only see local patterns, while the final layers are only equivariant to mirroring of the images. This turns out to work really well also on natural images. For example, we tested on STL10, which is a very, very small subset of ImageNet. And we see that even if these models are not equivalent to global transformations, they still have the typical data efficiency property of equivariant networks, where they have much stronger generalizations than standard convolutional neural networks. This kind of design is nice, but it's much harder to find the exact groups that appears at different scales, because like we don't know them often a priori, and it's maybe the question of identifying the symmetry groups at different scale is a bit ill-posed because it's not really well defined what a scalar is. So that kind of motivated our last work on where we kind of try to ask the question, how do we learn what are the symmetries at each scale in our neural network, or in general in our data sets? Or even how do we even relax these equivariance constraints, which sometimes, as mentioned earlier, can be over-constraining when the dataset doesn't have exact symmetries. Check the time. Okay. So that's the work I did with Lars in ICML this year. And what we try to do is essentially learn for each layer or for a whole neural network a probability distribution over a large, like the largest possible group we care about. And to do that, and we do that to try to identify relevant subgroups of which we may want to be equivariant to. So at a very high level, if we learn a distribution over, for example, the group G of rotations, and that distribution is uniform, it means we want to have equivariance to the full rotation group, and we fall in the previous setting. But if we want to have, maybe like the data actually doesn't have full rotation equivariance in 3D, but it has only equivariance, or it has only symmetries as a rotation around a certain axis. That is a subgroup of the 3D rotation group. And we, in that case, we kind of hope to learn a probability density function that is only supported on that specific subgroup, which is just a subspace, right? Of course, that is never going to work in practice because like everything is kind of continuous and smooth. We're never going to learn an exact step function that is 1 on the subgroup of interest and 0 everywhere else. So often we're going to have some some positive values also around that group. We kind of interpret that as some relaxed equivariance or like some kind of soft equivariance, which allows us to be kind of robust to small deviation from our equivariance group. This is kind of the goal we want to achieve. Now, how do we learn this probability function? And also, how do we use it to build networks which are equivariant only to the specific subgroups learned by this probability function? We try to do that simultaneously by basically looking back at our projection operator. If you remember, our projection operator looked like an integral over the group, right? And by integrating over the group, we basically enforce our kernel to satisfy the equivariance constraint for each group element, right? So essentially what we do is rather than integrating over the whole group as it is, we weight the integral by a learnable probability function. Now, if this function is supported only on a subgroup, this is going to be just identical to the projection only on the subspace equivalent to that subgroup. If the probability function is uniform, we recover the previous projection operator, but then we can interpolate between different groups in this way. And next few slides are going to be about how we do this projection and how we solve this integral. But yeah, spoiler alert, is yet again a Fourier transform. So basically by following the same derivations as before, we end up with the same integral we had before. But this way we don't just integrate each ERP independently, but we integrate them against our learnable probability distribution. And while before the function here was constant, now we have like a different function. Nothing changes, still a Fourier transform, but this time we get rather than a Dirac, like a delta function for the frequency 0, we get actually the Fourier coefficients of our learnable function, weighted by some normalization constant because the basis must be made orthonormal, of course. So comparing these to our previous approach with like a fixed equivariance group, now we don't have a diagonal matrix here with only ones and zeros masking out certain filters, but we have a kind of a block diagonal matrix containing the Fourier coefficients of our learnable distribution. Just to compare them side to side, the kind of functional form looks exactly the same, but we have like a bit less sparsity. We don't just have ones and zeros, but we have these Fourier components. I know this looks a bit abstract so far, so maybe let me try to make this a bit more concrete and give an intuition of what's going on here. Forget about convolution for a moment and let's just apply this to, or maybe like let's just do a convolution with a 1-by-1 filter. So we don't have a spatial resolution in our filter, but we have only a number of input channels and a number of output channels. If we do, and let's use the group of 2D rotations. If we just use normal equivariance constraint, we essentially recover the classical harmonic analysis and the classical Fourier convolution theorem, which basically tells us that after like some Fourier transform, our linear layer is just going to be applying some learnable weight at each frequency in input independently, but it's not going to mix different frequencies. That is our Shor lemma, if you're familiar with that. And that corresponds basically to this diagonal matrix containing our just ones that we saw here before. Basically, this matrix contains ones and zeros. It contains zeros where 2 input and output frequencies are different and ones when they are the same. So that's what it's kind of encoding. But when we actually learn distribution, so we don't only have the frequency 0, but we have some higher frequencies, we can now use these higher frequencies to map different input and output frequencies, which differ by that specific number. So like, for example, if we learn a probability which has a frequency 3 component, now we can actually map an input frequency 3 to an output frequency 0. This allows us to kind of smoothly break equivariance, because of course all these off-diagonal terms are not rotation equivariant. And basically the amount of band limiting in our learned distribution kind of controls how far we are from an equivariant network, because like the more frequencies you include, the less sparse this matrix becomes. So yeah, that's a bit the intuition of what's going on here. A few implementation details. All we have seen so far is differentiable, so we can actually learn these like our convolution filters, while we also learn the probability distribution by backpropagating through the projection operator. We have to ensure our learnable distribution is a probability, so we actually learn the Fourier transform of its log likelihood, and then we do some sampling and softmax, and again Fourier transform to recover the Fourier transform of a normalized distribution. We always initialize our neural network, our distributions to be uniform distributions, so we have like a strong prior at initialization that our model should be very equivariant, such that equivariance is broken only if necessary. And yeah, just to show you, like we can then tune some band limit of value to choose how wild and how flexible the learnable distribution becomes. The higher, of course, the more flexible and the more the model can break equivariance. Another nice thing is that because we have both the Fourier transform of the log likelihood and the likelihood function, we can easily implement things like the KL divergence, and we use that to kind of regularize our learnable distributions, because we don't want that the first layers are equivalent only to a certain subgroup, but then the final classification layers recover equivariance to the full group, because we know that's not possible by the way we stack layers. But the neural network could learn these distributions, and that doesn't mean the model is going to be again equivariant. It just means that the learnable distribution is not really interpretable. And one of the motivations here is also kind of finding out what are the symmetries. So we want basically that the deeper layers learn probability distributions that are only supported in the support of the initial layers. And that kind of works. We see that if we use KL divergence in the initial layers, we get something that is more equivariant, but in the final layers we get something that, look at the blue distribution, which has only positive values or high values, where also the first layer has it. But if we don't use the KL divergence, final layers don't really match the previous ones. So here we recover some high equivariance in places that before were not really equivariant. Another nice thing is that we measure the effective equivariance error at each layer. This is very rough approximation because we always work with the discrete images, so there's a lot of interpolation artifacts when we test this. So take this orange line more as an indication, not a precise measurement. But we see that when the learned equivariance at a certain layer has a pattern, the measured error has exactly the opposite. So when the likelihood is likely, the error is low, and when the likelihood is low, the error is high. This is a fairly constant function, so the error is also always low. The scale is different across plots, but this error is very low. And in the final layer here, we see that, for example, we recover only, we maintain equivariance only to the identity element, and this represents mirroring plus 180 degrees rotations, and that's also kind of the kind of error we measure. We evaluate our approach on a simple double MNIST dataset. We basically make up this fake synthetic dataset containing pairs of digits. So we always have these rectangular images, and we try to classify this number by, classify whether like the number from 1 to 100, 0 to 99. But we always apply only transformations at each digit independently. So we never rotate the full image, right, in this case, but we only rotate each digit independently. And that's basically to make it hard for a network that is equivalent to the global scale to classify them. Because like if a network is equivalent to 180 degrees rotations, it's going to predict the same label for this number and this, even if this is a 73, while a network that is equivalent only to local transformation can tell that this is a 37 and this is a 73, while being able to generalize over those variations. So yeah, again, we see that our model actually learn, if we test basically this method with O2 rotations of the digits independently, we see that the first layers of the network recover some local rotation equivariance. So this model at layer 4 has equivariance to 180 degrees rotations. So this is pi rotation. Reflection, this is a reflection. Red pi is a rotation and reflection. But the final layer can only be equivariant to reflection and rotations, because that basically maps this 37 back to a 37. Can you imagine that you get basically two numbers, you reflect them and then you rotate them back. Now you get just mirror the digits. So that's still like a global symmetry. And yeah, as expected, our method recovers this probability distribution in the final layer. This is a data set with no symmetry, so the final layer only has equivariance to the identity element, as expected. Very quickly, we try with different baselines on different variations. As expected, the proper equivariant models have lower than 50% accuracy because they cannot distinguish swap digits. We tried this on some three-dimensional datasets. I think I'm running out of time. Okay, a few minutes left. These are like 3D voxel datasets containing organs or like medical data. In particular, we see like on very symmetric datasets, we don't have like a particular difference with normal equivariant networks, but on datasets like this Synapse, which is fairly symmetric, but has a few non-symmetric relevant patterns, our method really outperforms a lot both standard CNNs and normal equivariant networks, but also like other baselines like RPP, which has some learnable way of breaking equivariance. The last datasets we play with is this smoke and jet flow simulation. This is a 2D dataset containing frames from fluidodynamic simulations of smoke in a box. So it has some local symmetries because like the physical laws are symmetric, but the box has a square shape or like a rectangular shape, which basically breaks the global rotational symmetries. We compare with many different methods in the literature that try to learn or break equivariance. And in particular, the RSteer method is from this Wang et al. Dataset, the dataset from Wang et al. Paper, which also proposed the dataset. And we essentially just take their steerable CNN as it is. We just plug our learnable projection operator and run it without any much tuning. And we always get basically best results or close to best results. So yeah, that's a kind of a quick overview of what we can do with steerable CNNs, both from hard inductive biases point of view, so how to build exact equivariant networks, and also from the point of view of how we can relax these constraints and how we can even learn them, or how we can exploit the different symmetries appearing at different scales in our data. And again, if you are interested in this, check out our library, this URL, and these are all the works that I based the presentation on. Thanks.
So thank you, Gabriele, for this nice talk. So it's time for questions. Actually, I'm gonna ask.
Sure.
So in the last part,
Yeah.
Have you ever tried to use, because you are learning Lambda, but Lambda is depending of the network, not of the.
Yeah.
Can you try to use like attention?
Yeah. I mean, so I want to maybe like look back at this. I cannot see.
Just because for some problems and some kind of image, some symmetries are important and
yeah. So I think that the overall idea is that is kind of nice and that can be generalized further. Is that what we do is that we have space of linear maps, right? And then we have a projection operator in the space of equivariant maps, and this projection operator is parameterized by this lambda function. If you have rather than convolution, you have MLP with a linear layer, you can do exactly the same way. We actually did that also with MLPs. You basically have to remove this dependence on X. The equation is the same. And the same could be done also for attention. You can take the linear layers of attention, right? Attention by itself maybe is not equivariant, but you can now replace the linear layers with basically this projection operator and try to learn that in the attention. We did not play with attention yet, but it's potentially.
My question was, lambda can be parameterized also by X?
Oh, that's an interesting point. We did not really try that yet. It could be possible. That is maybe like that would be quite maybe similar to a few lines of work that try to learn these equivariant frames. So they have this group convolution again as maybe the issue that you have to enumerate all the group elements, and people in the literature tried some approaches where you try to pick only a few relevant group elements conditioned on the input, right? And if you pick those group elements also in an equivariant way, you can do some kind of group convolution or just neural network averaging. So basically you apply this averaging operator over the full neural network by only sampling those few group elements. And that's like a very kind of hot topic now, like in the last year. That would be kind of similar. Like the difference maybe is that here we, by the fact that we use the Fourier coefficients directly, we can solve this integral analytically. That kind of boils down to plug in the Fourier coefficients in the right place. While in the literature, people typically either sample from this distribution or actually just predict a few samples and then use them to approximate the integral with Monte Carlo sampling, right? It would be kind of interesting to actually use these Fourier coefficients to solve that analytically as an alternative to that Monte Carlo sampling. Whether it's going to work better or not, it's kind of an empirical question, but definitely interesting.
Yes, thank you very much. It's really interesting talk. I also have some question regarding with Lambda. It might be a stupid question, but as far as I understand it, intermediates how you switch between the different subgroups. So I would assume it would be like it would jump between levels, that you immediately started as a continuous function. Could you comment a bit about how one could understand this smooth transition between different groups?
That's a good question. So of course, like this is like a kind of like a very hand-drawn simple example. Like ideally, right, you would like kind of, I don't know, Dirac delta function on the elements of the group you care about, right? That is impossible because the parameterizing these functions require you to have infinitely many frequencies, right? And also it's kind of basically a bit too optimistic to imagine we can learn such a high frequency function from the data, right? And things are always not perfect. The nice thing is that it turns out we actually don't need it, because if we look at the final equation, right, we don't, you can see here that we actually don't need all the Fourier coefficients of our learnable function, we only need the frequencies which actually do appear in our neural network. So typically, if you're maybe like here, it's a bit more clear, right? If your input and output features have only frequency up to 7, right? The maximum difference between them is, say, 7, right? So even if you learn a probability function that is band limited up to frequency 500, all the frequencies between 8 and 500, you're not going to use them actually. So what turns out is that you don't really need to learn a very sharp step function, because anyways, you only need the very the lowest frequency components of that. So that's kind of the interesting aspect that makes also this a bit more practical. From more like an abstract point of view and an intuition, what happens is that I kind of like to interpret this as not only just a learnable equivariance in the sense that we learn the subgroup, but it's more of also like a soft equivariance in the sense that we want equivariance to a subgroup more or less, and we also allow a bit of robustness and tolerance around it. So like it kind of makes sense to smooth down a bit things, right, and work with a bit lower frequency components, which kind of ensures that everything is a bit more robust and changes less drastically when the input transforms outside your symmetry group.
Thank you very much.
Sure.
So that's time for a short question.
Yeah, this is very interesting with the lambda there. You have as a base space, if you want to somehow make an operator there, do you have you can look at algebraic structures there. Are there some kind of addition? Because the class of operators you get is a really interesting one, because the Reynolds operators are projections and compact operators, and there's a whole category, if you can do it somehow an algebraic convenient way, of semigroups. Maybe you're aware of that. Then you can somehow use this theory to maybe approximate more the family. But
it sounds interesting, but I have no idea what is that. Can you repeat the name?
Semigroups in context of functional analysis.
Okay. Yeah, I'm not familiar with those concepts, unfortunately. But yeah, maybe we can chat later. It sounds like something very interesting. Thanks.
So let's thank our speaker again. Thank you. So now we have the lunch break, so we meet at 2 p.m. Then afternoon. Thank you.
Thanks.
The PDF of your talk.
Yeah, of course. Yeah. I might need like some days before, because I need to finish asking the approval for